are going to be looking at sound waves. So building off of what we looked at 7.1 to look at specific types of waves, in this case sound waves, and also looking at the properties of waves and how we can explain wave phenomena in terms of the properties of waves, such as wavelength, frequency, and amplitude. So some announcements. We have Unit 7 Quiz 1 this Wednesday, February 10th. What we're up to today, how does sound work, aka what is the physics of sound waves. Looking at beginnings of music from perspective of waves, what causes beats in music. And then what's the deal with trains, ambulances, police cars, fire trucks, / anything that has a siren. So the basic gist of sound waves, okay? Sound waves are longitudinal waves that result from compressions and rarefactions of a medium's molecule due to a driving force. Say a tuning fork, a guitar string vibrating back and forth, or a diaphragm in a speaker. So this all might seem a little bit strange, so let's break down each part bit by bit, okay? So the driving force, the tuning fork, guitar string, or diaphragm in a speaker, okay? So when any of these things vibrate, all right, let's say a tuning fork, the tuning fork is going to push outwards, which is going to push on the air molecules immediately around the tuning fork. Hence, that's going to be a driving force. It drives air molecules away by pushing on them through vibration, okay? So what's going to happen now is that our air molecules are going to collide with the air molecules next to themselves, neighboring air molecules, and that's going to result in compressions. In the area of compressions, that's where we have air molecules colliding, and during those collisions, those air molecules are transferring energy. Okay, specifically the energy from the tuning fork during the driving force, due to driving force, is transferred to air molecules. The air molecules during collisions transfers energy to neighboring air molecules, and that process repeats so on and so forth until the sound reaches its destination, say like an ear, where the energy is transmitted to the eardrum. Okay? So these are the compressions. The rarefactions are going to be a space where there's greater distance between our air molecules. Okay? So a rarefaction is the opposite of a compression. Okay? And because this compression and rarefaction is going to be occurring in this horizontal direction here, our wave travels horizontally, we're going to say our sound waves are longitudinal. If you want to imagine, the compressions are like when a slinky compresses. If you ever send a wave pulse on a slinky, you'll notice that the pulse causes waves to compress, and then, or excuse me, as the pulse travels, it causes certain parts of slinky to compress and other parts of slinky to spread out. And that's the same thing that's happening with our sound waves here, is that these compressions where air molecules are colliding, and these rarefactions where air molecules are spreading out. So the molecules collide via elastic collisions and transfer kinetic energy. This energy is the sound that arrives to ear. So during the compression part, like we see right here, okay, the air molecules are going to collide together and transfer energy, which results in energy transfer from our source all the way to our ear, what we're hearing, okay? So the compressions represent the amplitude. So right here in segment B, or photo B, this would be our amplitude right here. And this corresponds to high pressure areas where molecules are most displaced from equilibrium. If you recall, amplitude is a measure of energy transfer, or excuse me, better said, a measure of how much energy is being transferred by a wave. So the more energy that's being transferred by a compression corresponds to a higher amplitude, okay? So, on a molecular level, then, loudness corresponds to maximum displacement of molecules from equilibrium. The more our molecules move to compress and collide with other molecules, that means more energy is being transferred, and that's going to correspond to a louder sound that you hear. And then lastly, sound waves cannot propagate and thus cannot occur in a vacuum. The same thing as with heat. If we're going to have heat transfer to occur, we need molecules for the heat to be transferred through molecular collisions. The same thing happens with sound, is that in order for sound waves to propagate, there has to be molecules for energy transfer to occur through molecular collisions, okay? So as a result, sound waves cannot occur in a vacuum. So it's very similar to heat transfer in this way, except the only difference is that heat transfer requires molecular collisions from an area of high temperature to low temperature, whereas sound waves do not require an area of high temperature to an area of low temperature. So, wave phenomena. Interference and beats, we arrive to our first wave phenomena here. Okay? So two waves approaching can combine like numbers very briefly when they overlap, and we call this phenomena superposition. Superposition actually forms the basis for in higher level mathematics and physics, the area of mathematics called Fourier series, and it also forms the basis for quantum mechanics. Okay. Um, so constructive interference is when two waves overlap and the crests of both waves line up and the troughs of both waves lines up. The troughs and the crest will combine to yield a wave that has a larger amplitude than the two original amplitudes. Kind of like if we were to take plus 2 and plus 2 to get 4, 4 would be larger than plus 2 and plus 2 individually, okay? So we call this constructive interference because we're constructing a larger wave. Now, destructive interference is when we have the crest of a one wave lining up with the trough of another wave, and the crest of that other, and the crest lining up with the trough, vice versa. All right, excuse me, trough lining up with the crest. So crest lines up with trough, and then trough lines up with crest. And so as a result, it's like combining plus 2 and negative 2. You're going to get an amplitude that's smaller than your original wave, which in the worst case scenario can be a total cancellation. Okay? It doesn't have to be a total cancellation. It can be a wave that's just simply smaller than the two individual waves. But in the worst case scenario, you can get a total cancellation of the waves. And so because it's like we're destroying our wave, we call this a destructive interference. So something of interest here is that we don't have to have waves that are perfectly lining up crest to trough or crest to crest. We can have waves that have combinations of crest to trough and crest to crest, aka areas where the crest lines up with the trough and the trough lines up with, areas where one part of a wave, the crest, lines up with the crest of another wave, and other parts where the crest of one wave lines up with the trough of another wave. So what we call this is, so when this happens, what's happening is that the frequency of the two waves are similar but not identical. So as a result, there's going to be spots where the crest of one wave lines up with the trough of another wave, or the trough of one wave lines up with the crest of another wave, resulting, excuse me, I keep messing up here. I'm messing up my terms. So that's going to result in parts where we have the crest of one wave lining up with the crest of another wave, or the crest of that one wave lining up with the trough of the other wave. So that's going to result in spots throughout where we're going to have both forms of interference, resulting in what we call a beat. So we're going to have destructive interference resulting in some parts and constructive in other parts, which is going to cause a varying amplitude throughout. Parts where we have larger amplitudes than our two original waves, and in parts where we have smaller amplitudes than our original waves. So since I butchered this explanation here, let's take a look at a diagram that will help us visualize what's going on. Uh-oh. There we go. So this is what I'm saying right here, is that see how our waves are oh so very slightly offset? If we follow my mouse right here, we can see they're not exactly lined up. So as a result, we're going to have some areas, say right here, where the crest of one wave, the blue wave, say, lines up with the trough of the red wave. All right, again, we see the crest of the blue wave lines up with the trough of the red wave. And then we're going to have some other areas, okay, where we have the crest of blue wave lining up the crest of red wave. So we're going to have areas of destructive and constructive interference. And when that happens, we're going to have destructive interference, aka a very small amplitude, and then we're going to have constructive interference, a very large amplitude. And so that causes variations in amplitude throughout, and if you recall, amplitude corresponds to the loudness of our wave. That's going to cause a repeating periodic change in loudness of our wave. So we're going to have something quiet right here that gradually gets louder and then comes back down and gets quieter, loud to quieter. Of course, I'm not doing the best job of making the noises myself, but if you've ever played tuning forks before and you hear that whoa, 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 that's the same thing that's happening. In fact, I actually forgot we do have this here. So let's play this and see what it sounds like. So again, you can hear that whoa, 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 parts where sound gets louder and parts where it gets a little bit softer. So let's see how close we can get it. According we've been talking about, the closer our frequencies are together, the more drastic the interference should be. Yep, so you can hear that periodic loudness that's occurring. It goes from quiet to soft, or excuse me, it goes from loud to quiet, repeating over and over and over again, just like we see in our diagram right here. So here's a quick think, pair, share for you to answer. At this point, if you'd like to answer, please pause the video. If not, we'll proceed on to the answer. So two wave pulses, each of wavelength lambda, are traveling toward each other along a rope as shown. When both pulses are in the region xy, which are a distance lambda apart, so x and y are separated by a distance lambda, we want to know what the shape of the rope will look like. Well, if we take note right here, we can see that if we overlap these two waves right here, okay, we can see that the crest of the first wave is lining up the trough of the second wave, and vice versa for the trough of the first wave with the crest of the second wave. So as a result, when they overlap, we're going to have a total destructive interference pattern, meaning that nothing is going to happen in our XY segment. And I actually have a mistaken explanation right here. I say the first regions will combine constructively, while the second will combine destructively. I gotta go back and change that. That's how it's happening. We're having total destructive interference throughout. So next we're going to be looking at reflection, okay? So we have learned about reflection or we've seen reflection before in everyday life. You throw a ball off a wall, it comes back to you. A water wave hits off a wall, it reflects back. So reflection is nothing new to us, but what we're going to be focusing on here is why does reflection occur, okay? So first thing we establish is reflection will occur. Better said, inverted reflection, which is a specific example we're going to look at in this class, occurs when a wave reaches a fixed end, meaning a stuck ends that can't move. So like a guitar string, so guitars have fixed ends that are unable to move. So what's going to happen is that as our rope approaches the end, the tension of the wave is going to pull up on our pole / our fixed end, okay? And so as a result, by Newton's third law, the pole is going to pull downward on the wave, causing reflection. So the pole right here is going to, so tension will pull up on our wall, our fixed end, our pole, wall, whatever you want to call it. And as a result, the wall will pull down on the wave. And so that's going to cause the wave to become inverted, okay, and turn upside down upon reflecting off the wall. So at the end, a collision is occurring at the fixed end. So energy is going to be transferred out of the wave, causing the amplitude to decrease every time there is a reflection. We have this inelastic collision where energy is transferred out, and as a result, the amplitude of our wave will decrease since amplitude is a measure of the energy of the wave. And technically, if I want to be 100% accurate, this green force should actually be completely opposite 180 degrees to the red force, but for diagram purposes, it's not that big of a deal. Lastly, we arrive to the last effect that we're going to be looking at, which is called the Doppler effect, okay? So if you haven't put a name to the effect before, you've surely heard it before in everyday life. When the cars say like ambulance or something that's honking its horn passes by you, you will notice this increase in pitch. It goes, and then as it goes by you, that pitch drops off very sharply. It goes, kind of like we heard in the video here. Once more. All right, so what is happening? What causes this increase and sharp drop off in pitch? Okay, so first thing to note, okay, is that if a wave source approaches slash gets further away from the observer is going to see the waves taking less slash more time to reach them. Okay, let me pull up the diagram here actually, since the diagram will explain things better. So as our wave source, say an ambulance approaches a person, those waves, because of the decrease in distance between the ambulance and our person, those waves are going to take a shorter amount of time to reach our person, okay? So as a result, um, the period of the waves, the time between each wave reaching a person is going to decrease. Well, the time between each wave is, if we recall, the period. So as our ambulance approaches our person, the period is going to decrease, which, because period is the reciprocal frequency, is going to cause an increase in the frequency of the sound waves approaching you, which is why we see this this kind of building up of waves right here, so to speak, in layman's terms. Okay, so this frequency, this increase in frequency, is what you're hearing as the car gets closer to this. All right, and then after the ambulance passes by you, now the period between each wave is going to increase, so the frequency will drop off, and so that's that sharp drop off you're hearing where it goes as it passes by. Of course, I'm not doing it like anything like the video, so the imitation is not too good, unfortunately. And so as a result, because of this decrease in period and this increase in frequency, your wavelength will also decrease as well. Because of this decrease in distance, you're going to have more waves passing by you per second. So these waves are going to be more compactified. There's going to be a decrease in wavelength. Okay? Um, if you want to think about it, it's like if you hold a slinky apart and the person on the other end of the slinky starts walking towards you, the slinky becomes more compressed, representing an increase in frequency and a decrease in frequency, a decrease in period and wavelength. Okay? The important thing to note here is that the waves are not approaching you at a faster speed. The wave speed remains the same because the density of the medium remains the same. Remember, wave speed depends on density. So since the density of the airs remain the same, the wave speed is going to remain the same. Okay? So to give you an idea of that, it's like if I were to throw a ball at you from a distance of 5 meters away, and then I threw a ball at you a distance of from 3 meters away. If I throw it at you with the same speed, the ball that's thrown at you from 3 meters away will arrive in a shorter time, not because I'm throwing at you faster, but because the ball is being thrown from a shorter distance. So lastly, we have this think, pair, share here, okay? If you want, please pause the video now and go ahead and answer. If not, we'll proceed on to explanations. So it says, for diagram shown at right of a source S producing waves in a pond, which direction is heading? Please explain. Which point has the lowest observed frequency? Please explain. And then which point has the shortest observed period? Please explain. Okay? So for part A, all right, part A, the direction that our wave is heading, our object is heading, is going to be to the right, as the distance between waves is shorter to the right of S. All right, this diagram indicates to us that there is a shortened wavelength slash shortened period, which means that our object has to be heading to the right, since that's indicative of object S approaching, say, point C. So it's approaching point C because towards point C, the wavelength and period is decreasing, indicating to us that our source S is heading towards C. Next, we ask about the frequency, okay? Which point is the lowest observed frequency? And that would be point A because we can see this increase in period and wavelength, which corresponds to a decrease in frequency. Or in more layman's terms, there's going to be less waves passing through A per unit time than any other point. So there's less waves passing through A than there are through C, D, or B. And corresponding to that, point C is going to have the lowest period because as the distance between waves is shortest at this point, waves are going to pass through C quicker than through any other point. Again, this distance between S and C is decreasing, so distance between waves is shortest, corresponding to a decrease in period, meaning that the waves are passing by in a shorter amount of time. And this is our lesson on wave phenomena.